So we left off talking about probability, the probability of an event, the chances that an event will occur, right? And that's all great, but in context, we can do a little bit more with it. And that's when we start to talk about something called expected value, which is using this probability to determine the theoretical outcome of a game as either being a gain or a loss. So I define it more formally here to say that the expected value of some experiment that we conduct is the theoretical result one could anticipate the game could return based on the probability of each potential outcome, right? So the keyword is theoretical here. All of this is in theory. We're using it as a guide. Nothing about this is law, right? There are plenty of things, plenty of factors that could influence one way or another the actual outcome of an experiment that we conduct, such as with our example here. So if I consider a multiple choice test and there are 20 questions on the test, each question has 4 answers, right? So I have A, B, C, and D, 20 questions. And for the sake of this problem, all the correct answers have been randomly generated, right? So I'm not sitting here as the teacher saying, all the answers are B. I'm not making a pattern out of it. I've just scrambled all the answers, so this way all of the answers are equally likely to occur. And I want to know what the expected value of correct answers is if I just blindly guess A on all 20 questions. I walk in, I've never studied for this test, I didn't know what was happening. Teacher's making me take it anyway. I walk in, I just go A, all the way through. What happens? Well, if we consider our outcomes, right, I have 4 possible outcomes, and because they've been randomly generated, they are equally likely to occur. All right, well, I have each one of those being equally likely. The probability of picking A or B or C or D, any of them, is 1 in 4, right? 1 out of 4, or 0.25. So if I have a 1/4 probability of guessing correctly, and I do that for each of the 20 questions, then I should expect to get 5 of them right. Right, if I just randomly guess A, assuming that everything's been equally likely to occur, I should hopefully get at least 5 correct. This is my expected value, right? This is what we call our expected value. So can we generalize this? Well, of course we can. So in its more basic form, what do we see here? We see the probability of the event times, we'll call X, the number of trials. So we know what P of E is, right? This is the probability that an event E occurs. And then X, we'll say, is the number of trials, the number of times we go through this motion. So this is its simplest form because this is for one, we call it a binary random variable. And binary here just means I have 2 outcomes. I guess A, I either get it right or I don't, right? I have 2 outcomes. If we were to make this a little more complicated, maybe if I have multiple outcomes or multiple events, say, I would really just take all of these probability times x's and add them all together. So we're going to write it this way. We're going to write it as the sum of all of my P of E times x's. And this notation here, which maybe you haven't seen before, let me pick a better color that sticks out a little more. So this is the Greek letter sigma, and our sigma notation just tells us sum. I'm going to add up all of the probabilities times their number of trials. I'm going to add up all of my probabilities times their trials. I'm going to add up all of their expected values. That's where I was going with this. So that's all that means. It's the same process, right? So the process is the same, but we're just going to add up all the expected values. We should note that these are for what we call discrete random variables, and that just means that they are distinct, right? There are very clearly defined distinct probabilities for each one, right? Distinct outcomes. I can definitely get it right or I can definitely get it wrong. There's no weird wishy-washy gray area. So that's kind of expected value in its at its core. And then one of the ways we use this is to define if a game is fair. So a game is fair if the expected value of the game is 0. Right, so no matter what I wager in, if I have to put some sort of bet down, say, I put some sort of money into play. If I have an expected value theoretically of 0, then I have essentially an equally likely chance of winning as I do losing. Anything greater than 0 would say that my game is in my favor. Right, so maybe I'll put this off to the side here. My expected value is greater than 0, well, I would say that this is in the player's favor. This is in my favor. Because I can play, and over time and time and time again, if I were to carry this out over 100, 200, 300 experiments, events, trials, then I would actually still expect in the long run to come out with more money than I put down. If the expected value is negative, right, is less than 0, this is in what we call the house's favor. Whoever's hosting the game whoever's hosting the game stands to profit more than the player. So this is usually the case with a casino, right? We say that the house always wins. Right? One of the big things we hear in a casino is the house always wins, because if I were to carry this game out over hundreds and hundreds and hundreds of trials, the player could expect to lose money, which the house is, of course, making money on. So here's our carnival game here. I'm going to roll 2 fair 6-sided dice, and my roll determines the prize I get. So it's a very simple game. You're 2 dice on the table, you roll them, and whatever you get is what you win, right? So you pay $5 to play, and here's how it works. I'll use the laser pointer. So if you roll an odd number at all, you lose $5, right? You'd win nothing, so you walk away with the $5 in their pocket. You've lost the money. If you roll a 2 or a 12, you win $10. If you roll a 4 or a 10, you win $5, and a 6 or an 8, you win $3. We'll talk about why I set this up this way in a minute, but if you know anything about how hard it is to roll a 2 or a 12, you know why the prize is so big. Is the game fair? If not, how much should you bet for the game to be fair? Well, we know that a game is fair, we just said, if the expected value is 0. So let's find the expected value of this game. So the expected value of this game is going to be, we're going to add up all of my probabilities times their outcomes. It's my probability times their outcome. So we need to know the probability of rolling an odd number. And then the outcome is you lose $5, so we'll call this minus 5. And then the probability of rolling a 2 or a 12, and the outcome is you win $10. And then the probability of rolling a 4 or a 10, and you win $5, so you kind of break even. And then the probability of rolling a 6 or an 8, you win $3, so you actually win less than you put down in the first place. Great, so we got to calculate all this now. The probability that I win an odd number. So if I roll 2 6-sided dice, my odd outcomes are going to be 3, 5, 7, 9, and 11. Okay, well, how many different ways can I make a 3? I can roll a 1 on the first die and a 2 on the second die, or I can do the opposite, right? I can roll a 2 and then a 1. So there are 2 ways that I can roll a 3. Now keep in mind, if I roll 2 6-sided die, there are 36 outcomes. Right, 6 on the first, 6 on the second. So our fundamental counting principle tells us 6 times 6 is 36. So this tells us then that a 2, actually we're going to come back to this. How do I roll a 5? Well, I can roll a 1 and a 4, a 2 and a 3, or the opposites of both of those, right? A 3 and a 2, and a 4 and a 1. So there are 4. 7 is our most common, our most popular option. Sorry, I guess I should say more frequent option. 1 and 6, 2 and 5, 3 and 4, and then opposites of all those, 4 and 3, 5 and 2, 6 and 1, so that's 6 options. And then just to speed up the process here, there are 4 ways to get a 9 and 2 ways to get an 11. You can check those on your own if you want. Now, if I want to say the probability of rolling any odd number, what would be like saying the probability of rolling a 3 or a 5 or a 7 or a 9 or an 11? And what we learned in the last video is that if you have an or statement, you're going to add all of my outcomes up, right? So I'm going to add all of these together to say that the probability of, the number of odd outcomes from rolling 2 6-sided dice are 2 and 4, 6, 12, 16, 18. So there are 18 possible odd outcomes out of 36 outcomes total. So the probability of rolling an odd number is 0.5. So we're just going to go ahead and log that right in our game, right in our formula. So I have half of my rolls, if I were to carry this game out for hundreds and hundreds of trials, half of my rolls theoretically would result in me losing. This is already a bad start to this game. This is already a bad sign. But let's continue. So I want to look at the probability of rolling a 2 or a 12. This is an or, right? So we're just going to add. And normally I would say we need to consider the probability of rolling a 2 and a 12, right? Our or formula looks like this. But we know that rolling a 2 and rolling a 12 are mutually exclusive because there's no way that I can roll 2 dice and have it land on a 2 and a 12 in the same exact roll, right? So that little and piece is 0, so we can kind of just ignore it. Well, there's one way to roll a 2. That's a 1 and a 1. And there's one way to roll a 12. That's a 6 and a 6. So my probability of rolling a 2 or a 12 is 2 out of 36, or 1 out of 18, or 0.056. So I'm going to go ahead and keep my colors the same. That's not the right one. There it is. And log that into my formula as well, just to keep organized, right? So we're going to continue this process. I'll try to speed it up a little bit too. 4 or 10, so same idea, right? 4 plus probability of a 10. There's no way I can get them both, so I don't have to consider their what we call the intersection, kind of where they overlap. Well, there are 3 ways to make a 4. There are 3 ways to make a 10. So I have 6 out of 36, which is 0.167, so that's going to go up into my formula. And then finally, the probability of rolling a 6 or an 8. And we're just going to follow the same logic here. So there are 5 ways to roll a 6. There are 5 ways to roll an 8. 10 out of 36, which is 0.278. And that's going to go into my formula as well. It's the wrong color. There we go. So now I have my formula, right? We've done all this probability work. I'm going to add all these up, so I'm going to multiply everything together. I'm going to add everything up, and I've already done it to save ourselves some time. And the expected value of this game is negative 0.271. negative 0.271. So is the game fair? Theoretically, no. Theoretically, no. This game is not fair because my expected value is negative, right? If I were to carry this out over hundreds and hundreds and hundreds of games, or if I were to sit and work this game at Carnival, we would expect to actually come out with a profit, a small profit, because the player would lose money, but they're not losing a lot, right? We kind of say almost on average, so to speak. I'm using that kind of for lack of a better phrase. On average, the player loses about 27 cents per game, right? The odds of them actually winning and coming out with more money than they put down is slim. The only way they come out with more money than they put down is if they roll a 2 or a 12. Now, right? Because if they roll a 4 or a 10, they win $5. Well, they paid $5, so they're breaking even. They're just getting their money back. And if they roll a 6 or an 8, they get back less money than they paid to play. So they're kind of softening the blow, but they're not really winning anything per se. So, the chances, if you look at this game, are very much built in a house's favor, albeit just not by much, right? Because you have a fairly all right chance, or you have about a 16.7% chance of breaking even. But your greatest odds, hands down, are either walking away with nothing and just paying the $5, or walking away with less than you started with. So this game is not fair. Now, how much should I bet for the game to be fair? I just need to move this next problem down a little bit. So how much should you bet for the game to be fair? Well, where's my bet in this formula? My bet in this formula is right here. Right, this is my bet. And we have it written as a negative number because it's a loss, right? If I lose, I'm losing my bet. So I need my expected value to be equal to 0 for the game to be fair. So I've gone through and actually simplified the rest of this, right? Because this is all going to stay the same. The only thing that's changing is right here. So what this is going to look like is normally it would look like my entire, let's stay up here, right-hand side of this equation. Right, so I would have 0.5 times negative whatever the bet is, and maybe we'll call it B for bet, plus everything else. So I've taken the liberty of simplifying the everything else. It's 2.229. And this needs to be equal to 0. So if I were to go through and solve this for 0, right, I would subtract, maybe I would actually add over the negative b times 0.5 just to keep my positive coefficients. Divide by 0.5. And I would get a bet of $4.46. So theoretically, for this game to be fair, I have to put down a very strange amount of money, right? And this is a carnival, right? So I'm not going to be carrying around $4.46 to play every time. I'm just going to hand him a 5. Which is why, practically speaking, this game makes sense to kind of have this small loss. Maybe we could have changed the $3 to a $2.50 payout. Maybe that would have helped. So these are kind of considerations that you can make, and it all depends on what you want to design. Maybe you don't want your game to be fair, right? Carnival wants to make money. If you think about like the Washington County Fair right here in Rhode Island, then you don't want your game to be fair. You want it to be rigged a little bit in the house's favor so that the fair makes money. So it all depends on kind of your motives here. One last problem I want to consider. Raffles are particularly notorious for having really messed up expected values, because we don't know how many total trials there are going to be until this raffle is over. And by then it's too late, right? You don't know right away your odds of winning like you did in the carnival game, right? If I saw this carnival game, I could take a picture of the sign, maybe go off, do some work on my own, say, oh, this is rigged in their favor, because the probabilities are fixed. Whereas here, the probability is not fixed. It all depends on how many people play. So you're going to pay $5 for a chance to win $10,000, which is incredible. And I want to calculate the expected value of the raffle if a whole bunch of different numbers of tickets are sold. So let's see what happens if 50 tickets are sold. You bought one. Right, so you have your expected value on your one ticket. There's a 1 in 50 chance that you win the $10,000. And there's a 49 in 50 chance that you don't. And what happens if you don't? Well, you came out $5 poorer than you started. Right, so if I put this into my calculator really quick, I'm going to come out with an expected value of 195.1, or in the context of money here, $195.10. This would tell me, this doesn't say that, oh, if you lose, you expect to still win about $200. No, that's not what that's saying. What this is saying is it's still in my favor to buy this ticket because my odds are pretty good of winning, right? And the risk of losing $5 is greatly outweighed by the fact that I could win $10,000 and I'm only one of 50 people that could. So let's see what happens if I sell 500 and buy one. So now there's 1 in 500 chances of me winning, and 499 or 500 chances that I don't. So put this in my calculator again. And I'm going to come out with an expected value of 1501. So the risk is still smaller than the reward, but it's a much smaller reward theoretically, because my odds of winning are much lower, right? If we were to consider my odds of winning here, this is 0.02. This would be 0.002. And the last case we're going to look at is to sell 5,000 tickets and buy one. So now I have 1 in 5,000 chances of winning, and 4,999 out of 5,000 chances that I don't. So calculate one more time. Wait, that's not right. 5,000 negative 5. And I come out with an expected value of about negative 299. So now it starts to become more in the whoever's running the raffle's favor to run this raffle, because now they probably stand to make more on this than they gave out in the first place. And here my probability of winning would be 0.0002. So, raffles are tricky from a probability standpoint because you don't know what this number is going to look like. This changes throughout the night, and your expected value when you first buy the ticket is completely different than your expected value at the end of the night when they actually draw the raffle. And that's kind of how they get you. It's like, oh, we only have 10 tickets that we've sold at that time. They might have 3,000 by the time they pull the number. So raffles are actually a really interesting problem in mathematics and probability, because of exactly what you see going on right here.